Hello everyone. In this lecture, we're going to talk about trends in the periodic table. Okay, so first let's talk about what are periodic trends. So periodic trends are patterns in the periodic table that arise because of the arrangement of the elements. So the way the elements are placed in the periodic table results in these periodic trends. These periodic trends allow chemists to predict different properties about elements. And in order to predict these properties, we're going to be using the more simplified Bohr model. And so remember, we talked about this before, that the simplicity of the Bohr model comes in very handy sometimes. And in this case, it helps scientists determine a lot of different concepts about chemistry. These certain properties include atomic size, ionization energy, and metallic character. At least those are the three that we're going to be going over in this lecture. So what causes these trends? We've already talked about this, that these trends are caused by the arrangement of the elements in the periodic table. Remember that in the periodic table, elements are arranged in increasing atomic number from left to right and from top to bottom. So as we go from left to right, the number of protons increases. Remember that the number of electrons also increases as we go from left to right. But any electron that gets added, going from left to right, gets added into the same shell. But then as we go down the column, the quantum number increases, meaning any electrons that get added into a new shell. So as a result of the addition of these new shells for each row that we go down, the added electrons are farther from the nucleus, and therefore they're going to be much less tightly held. So we're going to be looking at these two different effects and seeing how they actually influence these periodic trends that we're going to talk about. All right, so we're going to begin by talking about atomic size. Atomic size is also called atomic radius, and it's determined by how far the outermost electron is from the nucleus. So in this case, this is the electron that's farthest from the nucleus. Its distance to the nucleus determines the size of the atom. All right, so first we're going to look at atomic size trends as we go across the row. So as we move from left to right across a row, atomic size decreases. So this means that sodium, for example, it's the biggest in its row, and as we go across, it gets smaller and smaller and smaller, and argon is the smallest in that row. And that's true for any of the rows. For example, lithium is bigger than beryllium, which is bigger than boron, and so forth, all the way up to neon. Okay, so now we're going to look at why that is. The reason is that as you go from left to right across the row, the electrons get added into the same orbit. Okay, remember we talked about this earlier. And as they get added into the same orbit, it doesn't affect their size much, right? Because they're being added into the same shell. But as we go from left to right, atomic number also increases, which means we keep adding more protons into the nucleus. The more protons that get added into the nucleus, the greater that nuclear pull is. And so those protons are able to attract the electrons more towards themselves, and as a result, they make the size of the atom smaller. So here's kind of a diagram to show that. Notice that each of these has 3 shells. Right, so here's n equals 1, n equals 2, n equals 3, and that's true for all of them going across. The difference is that as I go across, right, from sodium to magnesium, the second electron, so sodium has 1 in the last shell, magnesium has 2, aluminum 3, right, silicon 4, and so forth. As I go from left to right, the electrons are added into the same shell. But because I'm adding more protons into the nucleus, those protons are able to move the electrons more towards themselves, so they make the size of those orbits smaller. because they attract the electrons more. So think of it kind of as like a tug of war. The protons, the more protons that are being added, the more they're able to pull those electrons in towards themselves. The more they get pulled in, the smaller the size of the atom gets. Okay, so now let's look at the atomic size trends as we go down a column. As we move down a column or family, remember a family is another name for a column, atomic size increases. So as I go from up here, hydrogen, all the way down to francium, the size gets bigger and bigger and bigger. The reason for this increase in size is that we're adding a new orbit as we go down a column. And so as we add a new orbit for each row that we go down, we're filling a new bigger orbit. So the distance of that electron, it's farther from the nucleus. So that distance of the farthest electron increases as we go down the column. So here is a diagram that shows us going down the first column on the periodic table. Notice that lithium only has 2 orbits, but as I go one row down to sodium, I'm adding a third orbit. So that 1 valence electron of sodium is in the 3rd orbit. The 1 valence electron of potassium is in the 4th orbit, rubidium 5th orbit, and so forth. So as I go down the column, I'm adding a new orbit, and so that electron that's farthest from the nucleus is now even farther because it's a new shell was added. So the trend in atomic size is as we go down and to the left, the size increases. And as we go up to the right, the size decreases. So we would expect the element that's farthest down here on the left side at the bottom of the periodic table to be the biggest element in the periodic table, and the one here in the top right to be the smallest element in the periodic table. Okay, and then size just basically increases going towards the left bottom. Okay, now let's look at trends in ionization energy. First, let's define what ionization energy is. Ionization energy is the energy required to remove an electron from an atom that's in a gaseous state. First of all, we have to add energy to take an electron off. The reason is that that electron is attracted to the nucleus. It's being pulled in by the nucleus. If we're trying to remove that electron, we have to pull in the opposite direction of the nuclear force. And so that would require energy to break that attractive force between the nucleus and the electron. Ionization energy is the removal of the electron that's farthest from the nucleus, a valence electron. And notice that we said it has to be in the gaseous state so that there is no interference from neighboring elements on the electron that we're trying to pull off. Remember that when elements or atoms are in the gaseous state, they're far apart from each other, and so they don't interact or interfere with each other much. So ionization energy is the energy needed to make this a +1 charge, to completely take that valence electron away. All right, so let's go ahead and look at the trend in ionization energy as we go from left to right. As we move from left to right across the period, ionization energy increases, which means as we go from left to right, more energy is required to remove that electron from the element. So let's look at the reasoning for this. The reason behind this is the same as the reasoning we saw in the previous shell for atomic size, or in the previous slide. As we go from left to right, remember that atomic size gets smaller, and so there is a bigger nuclear pull, which makes it harder to remove the electron. So remember that as we move from left to right, electrons are added into the same shell or same orbit, but more protons are added into the nucleus. So as more protons are added, they tend to pull those electrons closer to themselves, right? Making that atom smaller. And actually the nuclear pull now is much greater because there's more protons in the nucleus. So those protons are pulling much harder on the electron, which means that much more energy is required to take those electrons off. So just like before, how we saw going across a row, the number of orbits is the same, right? All of these atoms here have the same orbits, but the number of protons in the nucleus increases. So the nuclear pull is greater, which means the force we have to put in to take that electron off needs to be greater also. Just makes it harder to take the electron off because the nucleus is pulling more tightly on it. So here is the ionization energy trend going across, right? It increases from left to right. And now let's look at the ionization energy trend going down a column. As we move down a column or family, ionization energy decreases. So it becomes easier to pull an electron off. And the reasoning for this is the same as what we saw for atomic size. As we go down a column, a new orbit gets added for each row that we move down. So electrons in the outermost shell are going to be farther away from the nucleus. So those electrons are going to be held less tightly. So as we move down a column, because we're adding a new shell, the electron that's farthest away from the nucleus is going to be farther and farther away moving down a column. And so the farther away it is, the less tightly it's held, so the nucleus is not pulling as tightly on it. So notice as on this figure, we can see as we move down a column, we're adding a new orbit for each row that we move down. And so this farthest most electron, the valence electron, is farther away from the nucleus as we move down, right? Compared to how close this electron was when we were farther up. So as we move down, the farthest electron becomes even farther away. That electron is not as tightly held to the nucleus, so it makes it easier to pull it off. So ionization energy decreases going down the column. And so the trend in ionization energy is that it increases as we move to the right and top. So the element with the highest ionization energy would be also the one that's the smallest in size, and the element with the lowest ionization energy is also the one that's the biggest in size. Okay. So again, note that ionization energy trends are opposite atomic size trends. As size increases, the ionization energy decreases. All right, so now let's look at metallic character. Metallic character refers to the tendency of an element or an ion to lose electrons in a chemical reaction. And remember, metals like to lose electrons, so if it has high metallic character, it likes to lose electrons, right? So this is what would happen. The metal, right, loses an electron and becomes a metal with a positive 1 charge. Notice what we see here is similar in concept to ionization energy. The difference is that ionization energy referred to the energy required to take an electron off, whereas metallic character refers to the tendency of that element to lose an electron. So they go hand in hand in that the lower the ionization energy is, the greater that tendency of that element to lose the electron, right? The less energy needed to take the electron off, the more likely that electron is to come off, and vice versa. So we're going to be looking at the same reasoning behind why an element would have a higher metallic character or the trend in metallic character. So the trend is as you move to the right across a period, metallic character decreases, which means that those elements towards the right have a lower tendency to lose an electron. And this makes sense because remember we said as you move from left to right, ionization energy increases, right? So electrons are less likely to be lost in a chemical reaction. So because ionization energy goes up, metallic character goes down. because as ionization energy goes up, those elements are less likely to lose an electron. Right? So notice that metallic character decreases as ionization energy increases. All right, so now let's look at metallic character trends as we go down a column. As we go down a column or family, metallic character increases. And again, the reasoning is the same as what we saw for ionization energy. As we go down a column, remember that ionization energy decreases, which means that it's easier to take an electron off. If it's easier to take that electron off, then that electron is more likely to be removed, which means that that element is behaving more like a metal. So as we move down a column, electrons are less tightly held, so more likely to come off. And so metallic character increases going down a column. All right, so we can just see here that as we move down a column, metallic character increases, right? And like we said, it increases because ionization energy decreases, and that's because those electrons are less tightly held, so more easily to be taken off. And then here is the trend in metallic character. So again, the element down here, I don't want to name it because I'm asking you a question about it afterwards. The one down here that is the greatest in size with the lowest ionization energy has the highest metallic character. The one up here, which is the smallest in size with the greatest ionization energy, has the least metallic character. All right, so here are some practice problems for you to answer. You can just pause this video, answer these questions, and then on the next slide, look at the answers. And here are the answers to those problems.